a water tank is built in the shape of a circular cone with a height of 5 meters and a diameter of 6 meters at the top. Water is being pumped into the tank at a rate of 1.6 cubic meters per minute. Find the rate at which the water level is rising when the water is 2 meters deep. So let's start by sketching this scenario. We have a circular cone. The base is going to be pointing up so we can fill it with water. And we are given some dimensions here. We are told that the diameter at the top is 6 meters. So that means that the radius at the top is going to be 3 meters. And we also know that it's 5 meters high, so the distance from here all the way down to here is 5 meters. And then we know that we're pumping water into this cone, so I'm going to illustrate the water level. So this is the level of the water at a given point in time, and we can indicate the radius here. So that's going to be the radius from the center of the cone, of course, out to the edge here. So that's your radius of the water level. And then the height of the water level, we're going to call that h. Like that. Now we're going to let the capital V be the volume of the water. So we have a rate. They're giving us the rate of 1.6 cubic meters of water is being added. So that's a volume that's being added. So we can say that the rate at which the volume is changing with respect to time is going to be 1.6 cubic meters per minute. And we are asked to determine the rate at which the water level is rising when the water is 2 meters deep. Okay, so we want to find dH dt when the water is 2 meters high. So h equals to 2 meters. Okay, so let's write down the equation for the volume of a cone. So volume and height are related with the following formula. V equals 1/3 times pi times radius squared times the height. Now the problem we have here is that we need to express volume as a function of height alone, and right now we have the radius in here. Okay, so we need to eliminate the radius, and we need to find a relationship between the radius and the height. And what we can do here is we can use similar triangles. So if we're going to sketch that out here, we have the situation where we have the height of the cone right there. So this is 5 meters. The radius at the top of the cone is 3 meters. And then we have the water level down here, where we indicate the radius with r and the height with h. So these are similar triangles. And so we can write the ratio of the radius over height for the water level. That ratio has to be the same as the ratio of the radius of the entire cone over height. And now we can rearrange this expression here and isolate r. And if we do that, we're going to get r equals 3 over 5 times height. So now we have an expression for the relation between the radius and the height, and we can use this expression here and substitute it in. So this can be substituted in for the r right there, hence eliminating r. So let's do that. So we're going to get volume equals 1 over 3 times pi. We substitute in our expression for the radius, which is 3 over 5 times height squared times height. And we can rewrite this or clean it up a bit and write it as 3 pi over 25 times h cubed. So that's our expression for the volume, expressed as a function only of h. So now we can go ahead and differentiate. We're going to differentiate both sides. We're going to differentiate implicitly. So dv dt equals the derivative with respect to time of the following expression. We can isolate the constant here. Or we can pull it outside the derivative. So we'll end up only differentiating h cubed. We'll differentiate h cubed using the chain rule. And so the derivative of the outside function is going to be 3h squared, and the derivative of the inside function is going to be dh dt. This can be cleaned up a little bit and written as 9 pi over 25 times h squared times dh dt. Okay, so what we want to determine here is dh dt, the rate at which the height of the water level is changing. So we need to isolate dh dt. So it's just a matter of rearranging this expression. So we're going to get, so actually let's first just write down our differentiated expression. So it's dv dt equals 9 pi over 25 h squared times dh dt. And now we can isolate dh dt. Okay, and that's going to be 25 over 9 pi h squared. Okay, times dv dt. So that's the expression we're going to be using. And at this point, what we can do is we can plug in our dv dt, which we know the dv dt was 1.6 cubic meters per minute. So we know dV dt, but we do not at this point know, well, we do know the height, do we? The height was 2 meters. We actually know it. We have the height and we have the volume at the rate at which the volume is changing. So we can just plug that in. So what we can say here, so we know height and we know the rate at which the volume is changing. So we can say dH dt is 9 times pi times, and h was 2, so it's going to be 2 squared. Right, because we wanted to evaluate it when the height of the water level was 2 meters. And then the rate, dV dt, was 1.6, like so. So this equals to 10 over 9 pi. So we can say that the water level is rising at a rate of 10 over 9 pi, which is approximately 0.4 meters per minute.